Hello, friends. So we will start working on more examples from probability, and we will dive more into conditional probability and compound probabilities today. So there is this school. There are 130 students. Out of these 130 students, 70 students take math, 45 students take history, 20 take both classes. So what's the probability that a randomly selected student takes math? What's the probability that a randomly selected student does not take math? What's the probability that a randomly selected student takes history? What's the probability that a randomly selected student does not take history? And then what is the probability that a randomly selected student takes both math and history? What is the probability that a randomly selected student takes neither math nor history? What is the probability that a randomly selected student takes math only? What is the probability that a randomly selected student takes history only? What is the probability that a randomly selected student takes math given that he or she takes history? What is the probability that a randomly selected student takes history given that he or she takes math? And the last two questions are the events of taking math and history mutually exclusive? And then, are the events of taking math and history independent? So we will start by constructing the Venn diagram for this case. So let's construct the Venn diagram. So there are students who take math, who take history, who take both history and math, and who take none of these. This is the most general case. So we start with the people who take both classes. 20 people take both classes. That goes right here. 70 people take math. 20 are here. That means 50 are here. 45 students take history. 20 are here, that means 25 are here. And then we add these up. 50 plus 20 plus 25, we get 95 students. And a total of 130 students we have. And 130 minus 95, 35 students out of this 130 students are not taking any of these classes. So, question number 1. What is the probability that a randomly selected student takes mathematics? That is 50 plus 20, 70 divided by 130. And if you simplify this, you get 7 divided by 13. What is the probability that a randomly selected student does not take mathematics? If the student is not taking mathematics, then we are, that's correct. We are interested in these two. So we can do 35 plus 25 divided by 130, which is 130, no, which is 60 divided by 130, which is 6 divided by 13. But we could also do the exact same problem by subtracting 7 over 13 from 1. Because if a student takes mathematics with the probability of 7 over 13, he or she is not taking mathematics with the probability of 1 minus 7 over 13, which will also give you 6 over 13. I don't care how you do it, as long as you do it correctly. And what's the probability that a randomly selected student takes history? Now what we are interested in is these two. So 20 plus 25, 45 divided by 130. And, well, you can simplify it if you want to. It's not needed. You can simplify it by 5. It's going to be 9 over 26, but it's not necessary. What's the probability that a randomly selected student does not take history? In that case, we are interested in these two. 50 plus 35, that is 85 divided by 130. Now, what is the probability that a randomly selected student takes math and history? That would be
95.
no, math and history. That means the two of them together. That's this one. So that would be 20 divided by 130. What is the probability that a randomly selected student takes neither math nor history? In that case, this is what we are interested in. 35 divided by 130. Now, what is the probability that a randomly selected student takes math only? Math only is this one. It's the same as math and not history. So it is 50 divided by 130. is the probability that a randomly selected student takes history only? That would be this one. 25 divided by 130. Now, when we come to the next question, things start getting murky. Math, this symbol means given history. What does that mean? A randomly selected student is given to take history. That's given. We know that a randomly selected student is taking history. What we would like to know is what is the probability that a randomly selected student is also taking math if we are given that he or she is already taking history. So this symbol, it means given.
Is it 20?
Math given history, so it will include 20, but we need to limit the sample space. We are not interested in all 130 students anymore. What we are interested in is only the ones who are taking history, because we are given that that student is taking history. This is all we are interested in. Does that make sense? So, out of these 45 students, we wanted 20. So, math given history is 20 divided by 45. If we are given that a randomly selected student is taking history already, that means we are not interested in anyone who is not taking history. That means we are interested in this part only. So when we select someone from this part, what is the probability that that person is taking math? That is 20 out of the 45. Now, what is the probability that a randomly selected student takes history, given that he or she is taking math? Now, this time, we are interested in this part.
20 divided by 70.
Very good. 20 divided by 70. Now, the next question is, are the events of taking math and taking history mutually exclusive? In order to answer this, we need to ask ourselves, can these two events happen at the same time? In other words, are there students who are taking math and history at the same time? The answer is yes. Since the answer is yes, are these two events mutually exclusive? The answer is no. They are not mutually exclusive. What does that mean? They do not mutually exclude each other. They are not disjoint sets. Okay? Yes. The answer to this question is no. Because there are people who are taking math and history at the same time, which means these two events can happen at the same time. Now the next question is, are the events of taking math and taking history independent? We don't know yet. We need to do a test. And that brings us to the test of independence. So, testing for independence. if two events A and B are independent. If events A and B are independent, then the following has to hold. Those two events happening at the same time must be equal to the probability of those two events happening at the same time must be equal to the product of their probabilities. So we will see. Now, the question is, are the events of taking math and taking history independent? So, what is the probability of taking math? 70 over 130. Very good. What is the probability of taking history? 45 over 130. Very good. What is the probability of those two events happening at the same time? 20 over 130. Yes. That is 20 over 130. Now, what we need to test is when we multiply these two, can we get this? So, is 20 over 130 equal to a question mark 70 over 130 multiplied by 45 over 130. They may be equal, they may not be equal. So let's see. 20 over 130 is equal to 0.154. This is 0.154. And on the other hand, 70 over 130 is 0.538. And then 45 over 130 is 0.346. Now, if we multiply these two numbers, what we get is this side will be equal to 0.186. And on the other hand, we have 0.154. So these two numbers are not equal. That means the answer is no. They are not independent. Since these are not equal, then they are not independent. Okay? What if I asked you one last question about this particular case? What is the probability that a randomly selected student takes math or history or both? Now, I don't have to give you this part. When I say math or history, that already includes math only, history only, or both of them. But I will still give you, just to be clear. So what is the probability of taking math or history or both? We are interested in these three things now. Make sense? So this is equal to 50 plus 20 plus 25 divided by 130. And that's equal to 95 divided by 130. Are we following, friends? Okay. Now the next question. In the next question, we will have two categories. So I will have to erase this. Erase the board, probably. It's going to be easier. I have this weather app. It says 18 feels like negative 10. I'm just exaggerating.
I mean, when it's windy, it does.
Yeah.
And cloudy.
And then I have this very big coat, right? I happened to not zip it up. So it was pushing me back. I had to turn and wait like this.
I used to walk to school when I was a kid. Walk
Yeah.
backwards. That's how loud I look right across the street.
I mean, I occupy a lot of space. I mean, because of Mr. Jose here. So it was pushing.
It does push.
Yeah.
Is this your first winter here?
Yeah.
Oh, okay. This isn't the worst. No, it was pretty light.
It's mild, right?
There's more.
Okay.
My phone used to be like 85 miles per hour. If that happens.
Okay, another marker is gone. Bye-bye. Okay, let's say we have a total of 100 students. 40 of them are wearing glasses. 25 boys are wearing glasses. And 20 boys are not wearing glasses. Okay? So we will calculate the missing entries in the table, and then we will calculate the following probabilities. When a student is randomly selected, what's the probability that that student is a girl? What's the probability that that student wears glasses? G for girl, GL for glasses. What is the probability that the randomly selected student is a girl who wears glasses? In other words, girl and glasses, that's the same thing. What is the probability that a randomly selected student is a girl or wears glasses? And then what's the probability that a randomly selected student is a girl given that she wears glasses? Or is a girl given that he or she wears glasses? And then what's the probability that a randomly selected student wears glasses given that she's a girl? And then are the events of being a girl and wearing glasses mutually exclusive? And the last question is, are the events of being a girl and wearing glasses independent? Okay, let's complete the table first. Since there are 40 students here, how many are here?
15.
15, yes. And then since there are 40 here and 100 here, how many students are here? 60. And then 20 here, 60 here, how many are here?
40.
40, yes. 25 here, 20 here, how many here? 45. And then 15 here, 40 here, how many here? 55, yes. Okay, what is the probability that a randomly, no,
I was just about to say that.
what is the probability that a randomly selected student is a girl? You're interested in these out of the 100 people. Yep, 55 over 100. Now, what's the probability that a randomly selected student wears glasses? 40 over 100. Now, the question will be worded like this. A student is selected at random, that has to be said. And then what is the probability that a randomly selected student is a girl who wears glasses? That means girl and glasses, which is what?
15 out of 100.
15 out of 100, yes. Now this one is a tricky one. Girl or glasses? Girl or glasses? Now, in order to meet this condition, a student either has to be a girl, these two, or has to wear glasses. Additionally, this one. Does it make sense? How are we doing there, Lisa?
Oh, I'm good. I had said 80.
Yes, okay, very good. So 25 plus 15 plus 40 divided by 100. That is 80 divided by 100. And that will be 0.8. Now, what is the probability that a randomly selected student is a girl, given that he or she wears glasses? Now, you are gonna limit the sample space to the people who are wearing glasses only. You are not interested in anyone else, because you are given that the student is wearing glasses. Out of these, you want the probability of those that are girls. So it is 15 over 40. Okay? And the next question, what is the probability that a randomly selected student wears glasses, given that she is a girl? In that case, now you have to limit the sample space to these people, because you are given that the person is a girl. So the denominator will be 55. Out of the 55, the people who are wearing glasses are 15. So 15 over 55. Now, are the events of being a girl and wearing glasses mutually exclusive? What do we need to concentrate on? Are there students that meet both conditions? In other words, are there girls who are wearing glasses? Answer is yes. That is not 0. So the answer is no. They are not mutually exclusive. Now, when we say, are the events of being a girl and wearing glasses independent, now we have to calculate. So let's calculate. What is the probability of being a girl? That is 0.55. What is the probability of wearing glasses? 0.40. 0.4 or 0.40. And then, what is the probability that a randomly selected student is a girl and she wears glasses? That is, girl and glasses. That is, yes, 15 over 100, 0.15. Now we are going to do our test. Is 0.15 equal to, is this equal to 0.55 multiplied by 0.4? Okay? On the left-hand side, we have 0.15. On the right-hand side, when we multiply this by 0.4, we get 0.22. These are not equal. Therefore, the events of being a girl or wearing glasses is not independent. It is just a statistical term, that's it. It doesn't mean anything else. Okay? I'm not trying to do gender bias here. Okay. much time do you have, Jim?
I have like 27.
Okay, good. Now the next question is a really important one. That's why I asked. So, I will need to erase the board. Are we all ready, friends?
Yes.
Good, thank you. So, now, the probability that it will be windy today is 0.8. Probability of winds today is 0.8. If it is windy today, then probability of windy tomorrow is 0.7. Okay, if it is windy today. If it is not windy today, then probability of not being windy tomorrow is 0.6. Now let's construct a tree for this structure. It's a tree. Okay? And then we will calculate several probabilities. So, for today, it can either be windy or not windy. Two cases. Dichotomous. Dichotomous means two cases, two possibilities. Tomorrow, windy or not windy. Dichotomous again, two cases. 2 times 2, 4. Our tree has to have 4 branches. But we'll go step by step. Today, it can be windy or not windy. Tomorrow can be windy or not windy. It can be windy or not windy. This is for today. This is for tomorrow. Okay? And then we will insert our probabilities. Windy today is 0.8 probability. That's the probability of this branch right here. This is 0.8. Now, if it is windy today, probability that it will be windy tomorrow is 0.7. That is 0.7 here. If it is not windy today, probability that it will not be windy tomorrow is 0.6, which is this one. Okay? This one. 0.6. Now let's complete the tree. Now, the branches that originate from the same point, probabilities have to add up to 1. There are 2 branches only. That's why this has to be 0.2. And it makes sense. If the probability of winds today is 80%, then probability of no winds today is 20%. And for tomorrow, if this one is 0.7, this one has to be 0.3. And then for tomorrow, if this one is 0.6, this one has to be 0.4. Now, the resulting tree has 4 branches. Okay? This branch corresponds to today being windy and tomorrow being windy. So, 0.8 times 0.7 is 0.56. Now, we are making an assumption here. Winds today and winds tomorrow are independent. That's why we can multiply them. That's an assumption we are making, okay? And then winds today and no winds tomorrow. That's 0.8 times 0.3. 0.8 times 0.3, that's 0.24. Right? Why? 8 times 3 is 24, and you need to have 2 decimal digits. So that's why it's 0.24. And then 0.2 times 0.4, that's 0.08. And then 0.2 times 0.6, 0.12. Now we will start asking questions. But let's first do a little analysis. Wind today, wind tomorrow. Wind today, no wind tomorrow. No wind today, wind tomorrow, no wind today, no wind tomorrow. 4 different cases. If I have done the multiplications correctly, these probabilities, these purple probabilities, they add up, they should add up to 1. So let's see. 0.56 plus 0.24 plus 0.08 plus 0.12 equals, this is 0.8, this is 0.2, and when you add, you get 1. So we're good. So, what is the probability that it will be exactly 1 day out of today and tomorrow will be windy? What's the probability that exactly 1 day, 1 day out of today and tomorrow windy? How do we do this? Exactly 1 of today and tomorrow windy. What does that mean? Either today is windy and tomorrow is not windy, or today is not windy, tomorrow is windy, right? So it is these 2 adding up. So basically probability of wind, no wind, plus probability of no wind, wind. That's what we are asking for. Are we following, friends?
Yes.
Okay. In that case, we add 0.24 plus 0.08, and it is 0.32. Now, what is the probability that both days will be windy. Which means this is the one we are looking for, right? Wind yesterday and wind today and wind tomorrow. 0.8 times 0.7, which is 0.56. We already calculated it. The third question, what's the probability that both days will not be windy? No wind today or tomorrow. No wind today and tomorrow. Yes, Lisa?
Would that be 0.2 times 0.3?
0.2 times 0.6.
Oh, 6. Okay.
That will be 0.12. Now, what is the probability that tomorrow will be windy given that today is windy? What is the probability that tomorrow will be windy given that today is windy? Now, tomorrow, if today is windy, we are interested in these two cases. Am I correct? That is our sample space now. If today is windy, regardless of what will happen tomorrow, these are the branches that come out from today being windy, right? So these two are our sample space. So the denominator of this fraction becomes 0.56 plus 0.24. Now, out of this, what we want is the probability of tomorrow being windy. That will be this one. 0.56, and this is equal to 0.56 divided by 0.80, and then you can, that is exactly equal to 0.7. But wait a minute, I already knew this. I didn't even need to do any of that. Because if it is windy today, I know that this is the case. I'm interested in this one anymore. I don't care about anything else. Okay? And if it is windy today, I know that this is happening already, and probability of windy today, probability of windy tomorrow will be 0.7. But you have to know both ways. Now, things will start getting murky, because I will switch these two. What is the probability that today is windy given that tomorrow is windy? It may not make sense in reality, but it makes perfect sense in mathematics. Let's see. Now what I'm asking is, what is the probability that today is windy given that tomorrow is windy. Now, if tomorrow is windy, which of these branches am I interested in? 1, 2, 3, 4. First one, I'm definitely interested in. If today is windy, no, if tomorrow is windy, I'm interested in the first one. I'm also interested in the third one. Okay? Now, this is my sample space. And out of these two, which one do I want? Today being windy. That's this one. So, the fraction becomes 0.56 plus 0.08, and in the numerator I will have 0.56. So this will be 0.56 divided by 0.64, and it's going to be 7/8, 0.875, whatever that is. 0.875. Now think of it like the following. Don't think of it like today and tomorrow. Think of it like Thursday and Friday. That will make better sense. What's the probability that Friday was windy, given that, no, what's the probability that Thursday was windy, given that Friday was windy? Now that makes better sense, because you're going to think of the past. Capiche? Okay. This is called conditional probability. Okay? Conditional probabilities. When I say probability of A given B, what I mean is conditional probabilities. Just 2 more minutes.
Okay.
Conditional probability. Probability of event A given event B equals probability of A and B divided by probability of B. Here's the logic behind it. Since we are given that B is already happening, the sample space is reduced to probability of B. But out of this, what you want is A and B happening at the same time. Got it? And that's exactly what we did there. And this is in fact called Bayes formula. Bayes' formula. Please excuse my English, I'm still an ELA. Okay? Okay, there is little bit time. There is little bit more material left, but I will cut it here. We have been going pretty well, so this is a good place to stop. There is a little bit more stuff, but it's going to be the beginning of next class. Okay? And In 2 weeks, you are having a midterm, just so you know. Before the spring break, you will have a midterm.
So I'm actually leaving the week before spring break. Is it required to be here? I forgot. Or do I do it on the computer?
Well, as soon as I finish probability, you don't have to be here. You're gonna do it online,
Okay.
and I don't need proctors or anything.
Okay.
So you'll be fine. Okay. Any questions, Lisa?
Have a good night.
Okay, good night.